Hi, everybody. Welcome to your notes video on compositions of transformations. This is going to look, or hopefully a lot of this will look familiar to you. We're just going to take what we did in the last section and kind of combine it or do more than one transformation at once. Okay, so here's what a composition of transformations is. Okay, and I'm obviously writing on the right side of my screen in your notes and I'm editing in Cami here. Okay, so a composition of transformations is when you do two or more transformations and then combine them into one transformation. Okay, um, it's very similar to what you did um, in your algebra classes when you were dealing with functions, and I'm going to talk about that in just a second. Okay, so one of the things that you want to be careful about when you are doing compositions of transformation is make sure that you pay attention to the order of the transformations, meaning like what order you do them in. So if you are supposed to do a rotation and then a reflection, that is different usually than if you do the reflection first and then the rotation. Okay, most of the time the order will matter when you're doing compositions. Okay, then we have this fancy thing called composition theorem, which basically just says that if you do two or more transformations in a row on a figure, then that figure will still be the exact same size and the exact same shape. Okay, so the exact theorem is the composition of two or more rigid motions. So two or more reflections, translations, or rotations is also in itself a rigid motion. Okay, so basically doing multiple transformations, okay, multiple rigid transformations in a row still won't change the size of your size or shape of your figure. Okay, so basically, really what we're doing is we're just taking what we did last week and maybe writing it in some different notation, and um, and then um, we're also going to do more of them just in a row on the same shape rather than just doing one transformation. We'll do a few in a row. Okay, so couple of things to a couple other things to tell you about compositions and the way that the notation is written. Okay, we use, if you remember briefly from last week in the videos, I taught you vector notation. Okay, which is kind of the crazy looking notation with all of the subscripts and the small letters, the capital T's, the R's. Um, so that is typically what we use when we're doing compositions of transformations because it's like shorthand and it's easier to write than the really long function notation. So usually we use function notation if we're just doing one transformation so that we can really easily track the points that we're dealing with. But if you're doing a composition of transformations, usually we use vector notation, okay? And when you use vector notation, and you can see some examples of how vector notation is written for a translation, reflection, and rotation. And you can also see on the right side of your screen a couple of those vector notation transformations put together into one thing. Okay, so it's very important when you're doing composition of transformations that you perform them. Like the order is you either go from the inside out, and I'll show you what I mean by that in a second, or reading from right to left. Okay, which is very similar to the functions that you did in your algebra classes. So I'm going to zoom in a little bit just so that I have some blank space here on this side. Okay, but I'm hoping that you remember from your algebra classes doing things like this, where they would say like f of x equals 2x and g of x equals x plus 3. And then they would ask you, what is f of g of x, right? Where you would put one function inside of another, okay? And you would always work from the inside out. You would figure out what this was first and then apply that to the outside function, okay? Or you may have sometimes seen them written as like F, and then a tiny little O, which stood for of, g of x, right? And this is what I mean by evaluate or read from right to left, that you would start with this function on the right, figure out what was happening here first, and then apply that to the outside function, or the one on the left. Okay, so it's basically the same thing, but we're just going to do it with transformations and with lines and shapes and things. Okay, so I'm going to do an example of interpreting some notation for you, and then I'm going to have you try one. And then I'll do an example of writing some vector notation from a description, and then I'm going to have you try one. And then we're going to talk a little bit about, and I'm going to try to show you this whole order matters thing. Okay, so here, right, what you can see on the left side of your screen is just the blank vector notation. Okay, so this, whatever's in parentheses, is the figure that you're moving. Okay, so that's the shape, the figure, the line segment, the point, whatever it is that you're moving. Okay, and remember, we always read from right to left. Okay, so start, what that means is that the T is going to be your first transformation, and then the lowercase r will be your second transformation, like in order. Okay, remember, with T stands for translation, this coordinate point here with the little vector on it, or the little carrots on it, this is how far you move in the x and y direction. And then the lowercase r, if you remember, is reflection. Okay, remember, capital R is rotation. Okay, the subscript here is your line of reflection. Okay, all right, so if I was to interpret or write out what's actually happening in this vector notation scenario, is I would say triangle, and I'm on the right side of the screen now, FYI, I'm writing in your notes. So triangle ABC is translated. So that's my first transformation, is translated 5 units right, because it's positive x, and 2 units down, because that's a negative y value. So that's what happened first. Then triangle ABC is reflected across the y axis. Okay. All right, so I'm going to pause the video here, and I want you to try this second one. Okay, remembering that capital R is a rotation. This capital O stands for origin. Okay, and that's the point that you're rotating around. It's the center of rotation. And then this number here is how many degrees you're rotating. Okay. Remember, if it's a positive degree number, you're going counterclockwise, and you have to tell us that in the description, right? Because we have to know what direction you're going. If it's a negative angle, you're going clockwise. All right, so I'm going to pause this quickly. Try this one out. Remember, you're reading from the inside out, so meaning you would do the rotation first and then the translation. Okay, so try this out, see if you can write this out, and then check back with me in a second to see if you got your answer correct. All right, folks, so you can see both on the left and right side of your screens that you have the completely filled in interpreted notation here. Okay, in the way that I wrote it on the left is like telling someone what to do, right? And the way that I did it on the right is saying this is what happened to that figure. Either way is fine, right? Like whether you use past tense, present tense, like it doesn't really matter, as long as you get the math part right. Okay, so here, what you're actually rotating and translating in that second one is a line segment. Okay, remember, we know it's a line segment because it has that notation over the top of the endpoints, those AB endpoints, but it doesn't have any arrows, which means that it's a line segment. Okay, so what we did is we rotated line segment AB 90 degrees counterclockwise about the origin, or you could have said around the origin, okay? Then we translated that line segment 4 units left and 1 unit up, okay? So we can also do this, I'm gonna skip ahead here. Okay, we can also do this with writing some notation, okay? So meaning what we just did in the last part of this in interpreting the vector notation is we started with the math language and we were trying to translate it, no pun intended, to translate it into plain English, right? Here, when you're writing vector notation, you are given plain English and you have to translate it into math speak, okay? All right, so and like I said, I'm going to write on mostly on the right side of the screen where you guys would write, but I'm going to do a couple little marks on here. Okay, so this first one says a clockwise rotation of 90 degrees about the origin, followed by a translation 1 unit right and 1 unit up. Okay, so that means this clockwise rotation comes first. Okay, and then this translation comes second. Okay, so, and what I'm rotating and what I'm transforming is this triangle right here, triangle ABC. Okay, so what I'm going to do is insert this as an equation so that way I have a little bit more control over what I'm writing. So I'm starting with triangle ABC, right? That's where I'm starting. Okay, and then I'm going to work from, you can remember, think of it as I'm either working from the inside out, or you can think of it as, actually, you know what? I'm going to get rid of it this way, and I'm just going to write it physically out. Okay, so I'm starting with triangle ABC. Okay, put that in parentheses. I'm going to model mine off of this one. Okay, this like kind of working from the inside out notation. Okay, what happened first was a clockwise rotation. So a rotation is a capital R, right? What comes next is what you rotated around, which they said there was the origin. So I'm going to put an O there, which stands for origin. And then it said a clockwise rotation of 90 degrees. Remember, clockwise is negative. Okay, so instead of putting positive 90 right here, I'm going to put negative 90. Okay, so that's my first transformation. Then I'm going to stick that in parentheses because I've got one more transformation, which is a translation. So capital T. And then I'm going to put my little brackets here, which tell me how far I'm moving for X and Y. Okay, so I'm translating 1 unit to the right. So that's a positive 1 for X, comma, and then 1 unit up, another positive for Y. Okay, so that's how you take the plain English and turn it into math speak. Okay, so I want you to try this second one. Remember that a reflection is a lowercase r, not an uppercase r. Okay, so give that a try and then check back with me and we'll see how you did. All right, folks, so you can see the answer there to that second one on both the left and right side of your screens. So we did a reflection about the line x equals 1 first, okay, which is this part here. Okay, let me do that in a different color. Okay, which is this part here, right? We're still taking triangle ABC, reflecting it over the line x equals 1, and then second, reflecting it over x equals 2. Okay, so on this one, I modeled my writing after this version of the vector notation, which is the one where you read from right to left, just so that you could see an example of both written out. Okay, yeah, so that's your writing vector notation. Right? So give me just a second. I need to reset my screen here because the last thing I want to show you and talk to you about is doing these things in the right order and what can happen if you don't do them in the right order. Okay, so I will be right back. All right, y'all. So I have some examples that are actually already written out for you here, and I want to show you what happens when you do transformations, these composition of transformations. Most of the time, if you do them in a different order, you end up with a different result, okay? So you can kind of see on the right side of your screen, it's filling up most of your screen here, that in both of these, we're starting with the same triangle, okay? Same triangle with the same coordinate points, okay? We're also doing the exact same transformations in each one, a reflection over the line y equals x and a translation of -2 for x and +3 for y. But in the first example, at the top of the screen, we're doing that, we're doing it in one order, and then in the second one that you see close to the bottom of your screen, we're doing it in a different order. Okay, so when you do the first version of this, where you do, so the original triangle is in red here. It's written in red. Okay, so the original triangle is here in red. If we take it and we reflect it over the line y equals x first, we get this blue triangle. Notice that it has one prime marker on each of these points to tell me that that's where it would be after the first transformation, okay? And then, so that's my blue triangle. And then we took the blue triangle and translated it 2 units to the left and 3 units up. And then we ended up with this purple triangle here, which notice has 2 dash marks on its coordinate points, okay, indicating that it's the second transformation that occurred. Okay, if we did a third transformation, those points would have 3 dashes, 4 dashes, and so on and so forth. Okay, so you end up with this purple triangle that's almost like off the grid. Okay, if you switch the order, okay, so looking down here at example 2, if you switch the order, so we're still starting with the red triangle, okay, if you translate it first, you end up with this blue triangle up here, which looks very different from this blue triangle in the first one, and then you take that blue triangle and reflect it over the line y equals x to get this purple triangle, okay? I'm hoping that what you can see is that obviously the shape ends up in a different spot, but it looks like the same shape. It's also oriented the same way. That happens a lot of the time when you're doing things like this, okay? But just goes to show you that the order that you do these transformations in does matter, right? Especially if you have translations involved, because translations will move figures closer to rotation points and further away from them, closer to reflection lines and then further away, right? Which means they end up moving a different amount of spaces depending on the order that you do those transformations in. So most of the time, the order that you do the transformations in does matter, which is why it's important that you write your transformation notation, your vector notation, that you write it carefully so that when it's read, that the order is correct, right? That you're doing these in the right order. Now, the last little bit I want to talk to you about is there are some instances when order might not matter so much. Usually that happens when you have a lot of the same type of transformation. So no mixing and matching, okay? It doesn't happen every time you have the same type of transformation, but it does a lot of the times. So like this first one is an example that if you did it in a different order, it actually would end up looking different. But what I want you to see in this one is that you can do 2 transformations and arrive at an end result, but you can also combine these transformations into one transformation, because that's really what a composition of transformations is. Like, could you get this red triangle to become this purple triangle without this blue triangle in the middle? And of course you could. You could just take it and shift it downwards. Okay, so sometimes doing two transformations is more complicated, or you could break apart a simpler transformation like a translation into two or three or four, like a combination of transformations, so that you get a composition of transformations here. Okay. Um, so this is just a little tidbit rule that if you have a double reflection over parallel lines, okay, then you're going to end up, that's the same as doing a translation, okay? And the distance, okay, that you will travel, okay, the distance that shape will travel is double times 2 the distance between your original lines. So like this here, the distance between y equals 3 and y equals -1, whoops, the distance is 4. And if you notice, if you track, say, from this red point C down to this purple double prime point C, there's 8 spaces between those points. 1, 2, 3, 4, 5, 6, 7, and 8. Double the distance between the reflection lines. Okay. So last example, because this is one of those times when you could do these two transformations in a different order and you would have ended up with the same thing, okay? So here, they took this original triangle, the one in red, reflected it over the x-axis to get this blue triangle, and then reflected that over the y-axis to get this purple triangle, right? I could have done this, or we could have done this in a different order. We could have reflected it over the y-axis first, right? And ended up with something that looked like this, C prime, B prime, A prime, and then flipped it up over the x-axis, and see how you would end up in the exact same spot, right? That purple triangle would end up in the same spot. Okay, this is another one of those types of transformations that you could accomplish with just one transformation. So if you have double reflection over two intersecting lines, like the x-axis and the y-axis, that's the same as a 180-degree rotation, which I'm hoping you can kind of see. You can get this red triangle over to where this purple triangle is without that blue triangle step in the middle by just taking it and swinging it 180 degrees around, all right? So that is essentially everything you need to know about composition of transformations. The key things to remember are, 1, order matters, right, which is what you can see here, and make sure that you know how to write your vector notation and what all of these stand for, right? Because once you know that, you can still use all of the rules that you learned for regular transformations and regular rigid motions that I gave you in the notes in that previous section and in that table that had all those rules written in it and how to transform your points. All of those rules still apply. You're just doing more than one rule per figure. All right, so the last video in this section is some practice problems with compositions of transformations. So I will see you all in the next video. Bye, everybody.